hold on. Well, please go ahead, Christian.
All right, welcome to the last session. Today is going to be conceptually a bit heavier. So I will most likely, I only want to bring across mainly the concept of a conformal family and fusion, and we'll see how much we can manage after that. So basically, after I have conveyed those two notions, I am going to probably relapse into Safari mode. But today, I think the concept of fusion is sort of like the one of the main things, and I hope that is something that you guys are interested in learning. But before we get there, let's make a brief recap. So what did we do? So at the beginning of last lecture, let's just see. A brief recap. At the beginning of last lecture, we started out with primary fields. Let's say primary fields. Primary fields phi. We argued that generally fields, any field can be, so field phi can be turned into a state phi in some Hilbert space. And today we're going to discuss this Hilbert space a bit more, if time permits. And in particular, if this state is primary, let me turn off this WhatsApp. It's annoying. And if we turn off, here, no, sorry. Now, if we demand that this state corresponds to a primary field phi, so this is called primary state, then, so the primary state satisfies this condition here, where n is positive. And we also, so for instance, and this one here, and it is an eigenstate of L0. This is just the holomorphic sector. And on top of these states, so as a reminder, the vacuum, so when H is zero, we also have L minus 1 and 0. And obviously for H is 0, also this one here is 0. So that was just an example. But more importantly, we learned that we can build Fock spaces which are called Verma modules on top of a primary. So how does that go? Well, we take the field phi and we act on it with the Virasoro modes. So we act with that on top, and that was just to remind you, that was just, where's the equation? No, that's too far. Here, these are these descendant states. Descendant states, in this manner, we build a Fock space, and that's called the Verma module. Okay. And then we counted these states. So we just took a look. Well, what can we do? And we found that basically what we should do is take partitions of the integer. So there's so the energy H, and then you add energy level +1, and then +2, and +3. And then the degeneracy at each energy level is basically given by the partitions of the integer n. Okay, so far so good. So that's what we did. And so this Verma module, just for future reference, so that you know, if when you encounter, this is also a conformal representation, or a representation of the Virasoro algebra. And mathematicians will call these things modules because they're vector spaces. But that's something that, if you insist, I can use that word. well, for Verma module, I'm always going to say Verma module. But for us, it's synonymous with representation. Okay, are there any questions regarding last lecture? Okay, that's promising. So then, starting from that, or moving on, we can define the notion of a conformal family. So the notion of a conformal family, let's make this an actual word, no abbreviations, conformal family. And when I say conformal family for a field, for a primary field phi, actually let's call this, that's for a primary phi, denoted. So what I mean by that is really just a shorthand for the primary state phi plus all, so as a set, if you will, all descendants. So this is a conformal family, and this is the conformal family for the field phi. Okay, and these things form a unit. They form one representation, form a representation of the Virasoro algebra. In fact, when we say conformal family, we're going to always mean an irreducible representation of the Virasoro algebra. And I'm going to explain in a minute what I mean by reducibility of a conformal representation of these Verma modules that we discussed. So just as a side note, that once we understood the notion of irreducibility, whenever we say conformal family, we actually mean an irreducible representation of the Virasoro algebra. Okay. So let's actually make this form an irreducible. Now we're going to see that in a minute. Okay, so the set, so I also the theory by I. All right. So this is this curly I. I'm going to use that for conformal family. So as an example, yesterday I briefly mentioned the Ising model, which is one of the earliest CFTs that had been studied. Well, it's been a model that's been studied for many reasons, but as a CFT and in also being part of the reason of the success of CFT, the Ising model is one of the first ones. Okay, so the Ising model has three families. So the set of conformal families, there's the identity field, there's the energy field, and then there is a spin field, which is called sigma. And if you've found time to make the exercise, to do the exercise that I suggested yesterday, then you have an idea what conformal weights they have. Oops, now let's go here so you can see. All right. So now let's talk a bit about the. So I'm gonna draw a sketch now, in a sense. So one way, perhaps it's a bit childish, but I find it very illuminating. One way of thinking about these conformal families is as, say, three houses, if this were a feudal society or whatever. Three houses. One is called the identity, for the identity family. So on top, there is the primary. then equivalently, there's going to be 1 for the other 2 families. Let's actually make this a bit bigger. The picture is going to be the same. It's just I'm going to make it a bit bigger. So let's copy this. So 1 is for the identity family. So this is the identity family, this is the epsilon family, and this is the spin family. There's always going to be a primary on top. And what we can do is we can act with L minus 1, with L minus 1 squared, L minus 2, and so on, right? So we can act and sort of generate a Verma module. We can generate the representation. And this is something that I didn't find time to truly explain, but the Virasoro modes are the generators of conformal transformations. So this, if you can't read this, this reads conformal transformations. So that means that if I perform a conformal transformation on a field which sits in the identity family, then it's only going to be reshuffled in this family. It's never going to mix. There's no mixing. No mixing. So this is actually, let's make it like this. There's no mixing between the families under conformal transformations. So the same thing can be done here. Wrong color. You can generate descendants and you can generate descendants here, but there is never going to be mixing under conformal transformations between them. That's just a statement that these are representations of the conformal algebra, and conformal transformations are just, well, generated by the conformal generators, Ln. Okay, so let's just put this here in the, so no, let's say no mixing of between families under conformal transformations. Okay, I hope that makes sense. If not, as always, you can interrupt.
Excuse me.
Yes.
Very quick. What is the difference between a conformal family and a Verma module?
Well, actually, it's just nomenclature. For now, well, Verma module is going to be really so by the end of this lecture, or by the end of, let's say, in 1 hour, you should have a clear idea of the sentence I'm going to say now. So when I say conformal family, I'm always going to mean the irreducible part of a representation. So in particular, a Verma module is not always going to be irreducible. In most of the time, it's going to be reducible. That means that we have to split off a subpart of the Verma module, which has no physical contribution. And then I get to the core, which is something irreducible. For now, these are just words, but as I hope, I almost, let me promise to you that by the end, like in 1 hour, you should have a clear idea of what that means. Okay?
Yes, okay. Thank you.
But good question. Good that you by now you should rightfully be sort of confused. Why do I need extra notation, right? Actually, maybe that's interesting. Let's add here. Let's add here in this. Let's make here a note after removing null vectors. Null vectors. Oopsie, vectors. And for that, so see below. Let's put this like here. See below. Okay. So now that we have the notion of a conformal family, we can discuss my favorite part, which is fusion. So when scattering fields, so this is something that unfortunately I didn't have time to explain operator product expansions to you guys yesterday, but I'm going to say a few words. So when scattering fields, mixtures can arise. Mixtures of families can arise. So what do I mean by that? So I said that under conformal transformations, there is no mixing, but what I can do, so I can make some sort of scattering experiment where I take a family phi1 and a family phi2, and I get some new fields. Yesterday, I told you that there is a notion called an operator product expansion, where I get a sum over a bunch of new fields phi k. For instance, in the Ising model, this would be sigma and sigma, for instance, would become something like the identity plus the other field, the energy field. So these are, and all of their descendants, so the families sort of can be included. And this coefficient here, this is an interaction strength between the fields. And if you go read the notes, then you find that basically you get this from, so C1 to K is proportional to phi1, phi2, phi K. So this is the 3-point function. We didn't discuss 3-point functions. We only discussed 2-point functions. But in the notes, you find the necessary comments for that. Okay. In general, so the coefficients C1 to K are usually difficult to find, but they're very important actually. So when we say we have solved the conformal field theory, we usually mean that we have access to these coefficients. But they're difficult to find, and sometimes, and this is the case for us now, sometimes we wish to answer a simpler question. So we wish to know something simpler. And that something simpler is, so let's formulate this as a question. What conformal families appear in the scattering? So that means, so the distinction, so let's say here of phi1 and phi2. The distinction is that, so C1 to K, this here can be some number pi or 16 or I don't know, gamma, the Euler number and stuff like that. It can be some random number. And sometimes I just want to know, like, if I bump phi1 and phi2 into, like, for example, like into do I get phi k? So here in this example, sigma and sigma, I can ask, is there, if I scatter sigma by itself, will I again get a sigma field, meaning a field of the conformal family of sigma? And you see here, I presented to you this notion here. This thing means that there is no sigma field. However, there is a 1, and then there is also an epsilon. So there are fields of the identity and the energy density field. families. And the answer to this question here is encapsulated in the concept of fusion. So let's make this a full sentence. Given two families phi1 and phi2, the fusion rules encode which conformal families appear in their, and here OPE stands for operator product expansion. Now let's just spell this out. Operator product expansion. And for the purpose, since I didn't explain this well, so usually this is abbreviated as OPE. Since I didn't explain this well, by that I just mean the scattering. Like I mean this diagram here, this vertex, what would you call it? Oh, this tri-vertex. Okay, so then fusion, I denote it like this. So I take the conformal family for phi1 and the family for phi2. And I introduce this new product, which I just denote star. And I just get, oops, this should be, let's call this not phi1, phi2, let's call this ij, because I did that also in the notes. I and j. And then here there is k. Oops. I, j, k, phi k. So these things here are integers. So nijk is a positive integer. So that really just means like it doesn't make sense that if I scatter phi1 and phi2 and I get negative multiplicity of phi3, I always get a positive multiplicity. So this is the concept of fusion. And this evidently, this looks like a product and we want to treat it like that. There is going to be a unit family under fusion. And you guessed it, that's just the family of the identity field. That means that if I fuse the identity family onto any other family, I get no sum. I really just return to the family itself. And this family, I forgot to say, well, let's just say this here. So this is going to be denoted by I equals 0. I equals 0 stands for the unit family from now on. And if you recast this here now in the sum notation of above, like for these fusion coefficients, oh, they're called, I didn't say this. So these are called fusion coefficients. That just means the following, that if I fuse the identity onto I, then the resulting family is going to be K. That can only be the case if I and K were the same family to begin with. Okay. So if you want, like here, this is sometimes done in the literature. I'm going to sort of recycle the diagram I made above. Well, let's actually make this like this. So I take family I take family J, and so I'm reading this from bottom to top, sort of like this, and I get family K. So this is Nijk. Don't confuse this with this diagram here. I mean, it looks the same as the one for the operator product expansion, but here I really just mean the fusion. That means, well, just the fusion as written here. This codes for an integer number, this diagram. Okay. So it does not matter if I fuse I and J and I get K, or if I fuse J and I to get K. That means, so this means that Nij K is the same as Nji K, and this is just commutativity. Commutativity of fusion. There's also associativity, well, associative. Associative, meaning that you can take phi I fusion phi j fusion phi k, and that should be the same as phi I fusion phi j fusion phi k. That's the same. If you want, you can try to work out in these fancy diagrams what that means. Left for you. By the way, I didn't draw these diagrams in the notes, but I think they're so simple, they're self-explanatory. So in what this here, so if you write this here in terms of these fusion coefficients, you get a constraint on the fusion coefficients. So the constraint that you find is that NIML NJKM equals the same as NIJN NKL. This is just a property. Okay. There is, so I said that, so I started talking about these interaction strength coefficients. And of course, I know that when the interaction strength of a field ij to couple, so sorry, of a scattering of I and j to never return a field k, then that means that, so that means if the fusion is 0, so I never get family K out of fusing I and J, then the interaction strength is also going to be 0. So there is going to be no coupling. So that's this statement. And also vice versa, right? So if I know that the fusion is non-zero, then the interaction strength is going to be non-zero too. There is something called the charge conjugate family. Charge conjugate family. And this is in the sense, really, this is meant in the sense of, I give you a negative electric charge and its charge conjugate is the positive electric charge, right? So now the idea is that I take positive and negative and I bump them together and I get neutrality. In the concept of fusion, we want to have that too. Unfortunately, it needs to be relaxed a bit. So if I take I and J and I get neutrality, like I said, the unit is going to be declared. Oops, that's not the right diagram. I fuse I and J and I get the vacuum. This is the right diagram. Then, so this is the same as Nij fuses to 0, then that means that J needs to be the charge conjugate. So what's the difference here? I'm going to give you an example in a minute where I'm going to explain that. But let me just give you a few more properties, which you all find in the notes. So if these properties right now make no sense, that's going to be okay. So for instance, what I can do is that if I have a charge conjugation down here, I can resolve the charge conjugation by flipping the other two indices. So here I have flipped them. And another property is that if all families which are in the fusion are charge conjugates, there should be no difference. So the result is the same as without charge conjugation. Now, let me give you an example. The fusion example, easing. And this is kind of stuff that the fusion rules, I believe, if you work with topological matter, you will encounter these things at some point or another. So the Ising family, or the Ising anyons, for instance, I think that's what they're called in topological matter. There you look at the fusion of the following families: identity, epsilon, and sigma. And so the first one is epsilon and epsilon. And you see from here that epsilon fuses with itself into neutrality, into the identity field, meaning that epsilon conjugate is the same as epsilon. Okay, so that's the charge conjugate field. So it's sort of real, quote unquote. Let's not call it truly real because that's not what it means. So then there's another one. So epsilon fuses with sigma. And you will always, so when you scatter epsilon and sigma families, so either the primaries or a primary with a descendant or descendant with a descendant, you will always wind up only with members of the sigma family. You will never wind up with members of the identity or with members of the epsilon family. Similarly up here, right? So when you fuse epsilon with epsilon, you will never get a member of the sigma family, and you won't also get a member of the epsilon family itself. All right, so that's one. And then the last non-trivial fusion is this one. Oh, I forgot to say, like here clearly zero, the family 0 is its own charge conjugate because it behaves like a unit. So if you fuse identity onto identity, it returns the identity, sort of by construction. And the last fusion here is sigma times sigma. And you see that the identity pops up, but it doesn't pop up by itself. There is another term, but we still call sigma its own charge conjugate simply because the identity pops up. And this is sort of like the only difference that I want to make with the analogy to electromagnetism. When I take an electron and a positron and I bump them into each other, I just get the neutral charge. I get nothing, right? Here in this case, I get neutral charge, but I also allow other stuff to appear. In that sense, I am relaxing this idea that I get absolute charge neutrality, if you will. You don't get absolute charge neutrality, if that makes sense. Okay, so these are the fusion rules. Are there any questions here?
Yes. So when we relax this condition at the end, is it related to the fact that we have a module and so there is no inverse, like in the
good. Yes, it
multiplication?
is sort of that. I think Saskia, the one who's chairing, she loves these matters. She can probably explain these things much better to me. But indeed, it's basically that. And currently there is there is, so I want to say that this is a version of a tensor product. It's not quite a tensor product for reasons that are outlined in the notes. But this fact appears over and over also in modern research, in particular if you're interested in symmetries. There's something called non-invertible symmetries, and there you have basically stuff like this going around. So this sigma will give rise to a non-invertible symmetry. But I don't know quite yet, but I think Hultat will talk next week about that.
Thank you.
Okay, so there is one more thing here. Well, there are many more things, but I'm just going to restrict to one more thing. So it is customary to introduce I by I matrices. Let's write like this: fusion matrices. And these fusion matrices, let's call them Ni, have coefficients, which are just the fusion coefficients, and done in this way. So this is the matrix Ni, and it has components Jk, and these take values in I times I. And that's just Nijk. So these are the components. And it turns out that if you take the fusion matrix for the charge conjugate of I, it really is just going to be the transpose of the original one. So in particular, if you have fields like epsilon, which are self-conjugate, or sigma, which are self-conjugate, then these things are going to be symmetric matrices. Okay, so there's an exercise which I forgot to write down the number. Give me a moment. What's the number of this exercise? Oh no, 5.7. There we go. Exercise 5.7. Show so that you can take these fusion matrices, Ni and A and J, and they themselves, we say that they furnish a representation of the fusion algebra, Nk. And the exercise is to show this. So for those of you who are not as mathematically inclined, then what I just said, that they furnish a representation of the fusion algebra, just means that if you look at the equation that I just wrote down, it looks exactly as the equation of fusion, as the one up here. Where is it? As the one up here, where if I just replace the family symbols by the fusion matrix symbol, then I just have exactly the same equation. So that's what it means to furnish a representation of an algebra, or in this case, the fusion algebra. And in the note, so much more stuff. And in particular, so now it's time to move on to the notion of irreducibility, unless there are other questions for fusion.
I have a question. Given a conformal family, are we always guaranteed to also have its conjugate, or at least one conjugate?
Right. We're going to assume that the identity field is always present. And let me see. Are we always guaranteed that there is a family? Yes, we're always guaranteed that there is the charge conjugate family around. But how do I see that? I'd have to think about that. But probably it's just juggling with these constraints. We can make that into an exercise. I'll think about it, and next week I can tell you, or you can approach me and we can talk about it. But so I know that the charge conjugate family is always around. And I think that really just hinges on the fact that we're assuming that the identity family is always around. And the question is like, can you show that? All right. Next point. So let's talk about Hilbert spaces in CFT. CFT. So the aim here is modular invariance and CFT spectra. But as time has progressed already quite some, I will not really talk about modular invariance. Instead, I will just highlight a few features. What I really want to discuss now, because I promised it, is sort of irreducibility of a conformal family and, well, reducibility and irreducibility, how to think about that. And then I'll talk a bit about how to take these irreducible representations and assemble them into a physically meaningful spectrum. But I'm afraid that 45 minutes won't be enough to really turn that into a proper, like a complete discussion. Like I said, it's going to be more a bit of a safari. Okay, let's get going. So 6.1 is conformal characters and null vectors. So conformal characters and null vectors. So observation. I've already said it. And now we're going to be concrete. Verma modules can be reducible. Okay, let's start with an example where I'm just going to confront you with a problem, and then we're going to lead this problem into, we're going to rephrase that as reducibility of a module. That means reducibility of a representation. So let's start with the identity family. So we had the Verma module for the identity family. Like I said, identity is going to be denoted by 0. So that's the family for 1. Okay, and so when we go, let's just run the same game that we did yesterday. We construct descendants. We construct the Verma module. Here we keep going. Then there is L minus 2. Oops. L minus 2. And here we keep going. And now, maybe some of you spots a problem. If we had more time, I would ask you now to spot the problem. But there is a contradiction with something that I said yesterday. So yesterday, I said, well, not a contradiction. There's something that we haven't taken into account yet. This piece here, by conformal invariance, this vector is 0. So I said yesterday, global conformal invariance means that the ground state, the vacuum state, needs to be invariant under the global conformal group. And this guy, L minus 1, is actually the generator of translations, which is a subpart of the global conformal group. That means that this guy is secretly 0. So it's not there. And in conclusion, nothing that follows after it, nothing that is built on top of this guy is going to be present. So they're all gone. They're all, well, not there. Okay. So how to think about this? Like all the other states, like built on L-2 and L-3 and so on, they're there. They're okay. Like in particular, we figured out that this guy here was just the energy momentum tensor state. Okay, more generally, so this was an example. More generally, let me draw a picture. I can start from a primary phi, and I'm just going to draw a cone. This is like the cone of descendants. This is the cone of descendants, meaning that here I act with L-1, I can act with L-2, and so on. And it can happen, say, let's consider a state, let's call it psi. This is going to be some descendant of phi. And on top of it, I can again act with Virasoro modes. But it can happen that in general, that a descendant, and in this case, it's psi, is once again primary. That means it is of the form of the Fock space that we created, but at the same time, it is annihilated by the LNs. That means in particular, so for instance, if I have this point or I have this point, then there is some combination of Virasoro modes that I can take with some positive index n, so that I can revert back. So I can always go down in the cone. Just like I can go up in the cone by increasing energy, I can always go down in the cone by decreasing energy. But if I'm here, so if I'm at psi, there is just no way. So because of this condition, I cannot go back. So this is like if you study black holes, it's like an event horizon. You go inside, but there is no way you can come back out. So this is denied by this property. So yeah, let's put a box or an ellipsis, whatever. All right, so that's peculiar. And moreover, and this is an exercise, you can show that psi stands orthogonal to any state, to any vector in the Verma module of phi. Okay, so this is very dramatic, right? So it means that nothing inside here really talks to anything in the Thiele area, right? So they are discommunicated. So psi does not talk, in quotes, to the Verma module phi. But that means that in principle, I can ignore it. And what we do in practice is that we just set psi to 0 and its descendants. Okay. In mathematical terms, what that means, right? So these are transformations of the algebra, right? It means that the orange area forms its own submodule, its own subspace, its own invariant subspace. So this is in group theory language, this would be a block diagonal decomposition where these two blocks do not communicate via the conformal group. Almost. Because you can hop inside from the blue-green area, you can hop inside the orange area. Okay, so this is what we mean by reducibility, and to make it irreducible just means that so if there are several null vectors, because it can be that there are no null vectors at all, but there can be several null vectors too. So this is repeated for every null vector in a representation, in a Verma module. And what that means is that after basically ignoring all the null vectors, so we have the Verma module for phi, and then we sort of drop all null vectors. There's going to be a rest. And this rest is always going to be connected. So that means that by conformal transformations, I can take any state in the cone to any other state in the cone. They're so to speak always connected. And that's the irreducible. Let's call this core. That's by no means standard to call it irreducible core. You just say irreducible representation, but I think it clarifies what's going on here. So this is the irreducible core of the Verma module of phi. And that's what we're going to mean by irreducible representation of the conformal family, or sort of that's what we mean. When I say conformal family, I'm going to mean just this irreducible stuff. I'm going to exclude from that notion the null vectors. Okay. So whoever had the question before about why I need the notion of family versus Verma module, I hope now it's clearer what is going on. Okay. Are there questions? Like in essence, really what you just have to remember is this picture that there is a subspace which is basically keeping to itself.
Maybe just with reference to the previous example. So in that case, would so the descendant, which is a primary field, would be the L-2 of the.
No, no, this guy here, for instance. Yeah, good. Let's clean this up a bit and go now from start. Right? So this guy here, oops. This is now psi. This is the null vector. And this here, everything that comes after, let's just like that, is sort of this cone here, this orange cone. And we're instructed to just ignore all of that.
Oh, okay, cool.
All right.
So if we didn't kind of assume that L-1 of the vacuum was 0, we could like prove that it was a submodule, or it generated a submodule.
Well, in this case, it's sort of by assumption a submodule. Like this is the only example where there's like by assumption, because I need a state. Like the statement of a CFT, or more generally, I give you a quantum field theory, and the statement that it is subject to a symmetry means that there is one state, which is typically unique, probably always unique, which is going to be invariant under the symmetry algebra, right?
Right.
In this
Right.
case, we need to make a distinction between global and local symmetry algebra, and so we're going to stick with the global symmetry algebra. The local symmetry algebra generates the descendants in the spectra, right? But you see that here for the vacuum, it's sort of by assumption, it's that this state needs to vanish. Otherwise, the state 0 that I'm declaring does not have the desired properties to be the ground state in a conformal field theory, not even in a Poincare invariant, or just translation invariant theory, right? Because L-1 is just the generator of translations. But in general, so your question is still valid. You can look into there's this yellow book, Conformal Field Theory, by the thick one. They developed the theory of null vectors in much more generality than I can do here. You may have fun reading that.
Okay, thank you.
Okay, so now I'm going to be a bit brief. So now we want to count states. So yesterday we counted states in a Verma module. And now we want to count states in an irreducible representation. So, and that's the notion of a character. So, or these things are going to be called characters. So character of a family phi I. And that is sort of, I put this in quotes, a mini partition function. Mini partition function for the family phi I. So think of a partition function. What is a partition function in statistical mechanics? Well, it's just you take a Hilbert space and you trace over a thermal density matrix, which is just e to the minus beta h. Beta is some inverse temperature. And in the notes, I call this beta 0 because further, like next week, I'm going to talk about boundaries and beta is going to be labeling something else. But now it's just an inverse temperature. You're all well aware. In CFT, we typically write e to the minus beta as q for reasons that are also explained in the notes. And now what we're going to do, so keep in mind that the Hamiltonian is L0 plus L0 bar. And now I'm just going to talk about a holomorphic sector. So I'm just going to take a holomorphic conformal family. So one thing. So I is going to be taken from so I is going to be taken from the set of conformal families, and I'm going to trace and take sort of L0 minus C over 24. And I'm going to trace over the irreducible, like the irreducible the representation of the conformal algebra for I. So what's the deal here? Well, the Hamiltonian, the holomorphic part is just this L0. This here is just the temperature, e to the minus inverse temperature. And this piece here, for now, there's a reason it's there. It's going to guarantee nice properties under so-called modular transformations, but we won't discuss that today. So for purposes of now, let's just think of it as ad hoc and a convention. Okay. All right. So we have basically done this for a Verma module. For a Verma module, we can also write down a character for the same family. Let's just do that. So we, just like yesterday, so let's see, c to the minus 24. Let's actually start differently. So we counted states. We started from a primary state, and we had this result here, q to the n. And n, so we had h plus 1, h plus 2, h plus n. When we counted in the table, we counted energies. And here we have, on top of that, we have So we have L0, right? So what we're missing here is we just have the N piece, but we're missing the first piece, and that's sort of also included here, which is Q to the HI minus C over 24 is really just this addendum that's running around. So, but this is now sort of counting states, like computing this character for a Verma module. We have done that. And now if you want to count states in this fashion, in a mini partition function for the irreducible core, well, what you're instructed to do is really straightforward. You take so this is supposed to be the irreducible core. So when I just write I instead of VI, I mean the irreducible piece HI. Let's just write this character of HI. And what I mean is I'm going to take the Verma module. I'm going to take all the character of the Verma module, counting all the states in there, and I'm just going to subtract. I'm going to subtract the Verma modules the characters for the Verma modules of all null vectors. So K runs over all null vectors. And this is how you count states for an irreducible representation of the conformal algebra. There is a subtlety which I point out in the notes. I can tell you. So sometimes it can happen. Let me just make a brief recycling here of the picture. If you have a second null vector, say here, let's make it in a different color, not blue. Let's make it. It's purple. It's not super duper visible, but it's what we have right now. It may happen that cones of, so that there is an overlap here. And in that case, there special care needs to be taken, but I won't discuss this. This is in the literature that I referenced. And so when these cones do not overlap, this is the final result. In most cases, in interesting cases, they do overlap, and you have to work harder. For instance, in the Ising model, I give concrete expressions for these characters in the Ising model in the notes, and they're going to be some infinite series. But for now, I actually want to move on because there's still two important things I want to drop, and once I have dropped them, I will slow down a bit, and we can talk about things that are unclear. Okay, so 6.2 is now structure of the state space. Okay, in the Ising model, for instance, we have fields identity, epsilon of z and z bar, sigma of z and z bar. And now I'm going to always talk about holomorphic and anti-holomorphic sector. So each of these fields here, sort of, it has, if you will, since it has h equals 1/2 equals h bar, essentially it's, if you want, a product of two conformal families, one for the holomorphic sector, one for the anti-holomorphic sector. And in general, a theory has several primaries. Let's call them phi and I and I bar. So this depends on z and z bar. And the Hilbert space of the full CFT needs to basically know about every single representation for holomorphic and anti-holomorphic sector. So okay. So what is this equation? So forget about the z for a moment. Actually, let's just erase the z for a moment. So each of these fields here, so this is the I, this corresponds to here, and this is the I bar, this corresponds to its own representation. So this field phi I bar is basically giving you like a tensor product of two irreducible representations. And now I throw in, so it can happen that the same field occurs more than once. It can occur several times, I and I bar. And it can also happen that, so for instance, in this example here, we have h equals 1/16 equals h bar. So here it's always that left and right moving fields are going to be coupled with the same conformal dimension. That means that they are spinless. It can also happen that you have fields, for instance, that are, let's make up a fiducial field, not psi, capital phi, which would be something like epsilon on the holomorphic sector and sigma on the anti-holomorphic sector. Now let's call this phi 1/2. That's epsilon on the holomorphic sector and phi 1/16 on the anti-holomorphic sector. That can happen. And that's why this coefficient z is in principle general. So it's going to be a matrix if you look at this. It's going to be so a capital I times capital I matrix. So we're going to demand that the identity is unique. So this is unique. That means that the coefficient for 0, 0 is 1. And now we can construct a partition function for this. And the partition function, I'm just going to drop the result, is really just going to be the trace over, and now I introduce again this bookkeeping device, which you can think of as e to the minus inverse temperature. But there is much more to it, and I refer you to the notes. And here we go. Q bar, and now here Q bar is indeed the complex conjugate of Q. So I write Q star. I'm mostly going to write Q bar, but here keep in mind this is not meant as with Z and Z bar, where they're meant to be independent. Here they're actually meant to be complex conjugates of each other. Okay, so this is really meant in the following fashion. This is meant in the fashion as that. So usually, so how do you arrive at this expression? I'm just going to sketch this, but there's a much larger discussion in the notes. So usually we write let's put a Q and Q bar here. This is for later. We write trace of e to the minus beta h. And in CFT, this basically becomes, so you have to do some adjustments, which I don't have time to discuss now. But in CFT, this basically becomes this here, L0 minus C/24. Let's not make it equal. Let's make like that, because it's not equal in general. You get this expression. And this is how you see that. So when you take the Hilbert space here and you use the decomposition that we had up here, and you just plug that in, then you see how this expression here arises, sort of, because that's really it just looks like the characters. It's just what it is. Okay. The coefficients Zi, so these coefficients are constrained. Are constrained by modular invariance. And this is an important concept, which I will not have time to discuss. The upshot is this. There is I tau and Q bar as e to the function of the theory, now I'm writing this in terms of tau and tau bar, is the same for different configurations of tau. And this is something that comes from analyzing conformal field theory on the torus. But like I said, now it's sort of going to be a bit of safari. The reason is that I want to introduce, so I want to pay particular attention to this one here in a minute. So how do you do this? Well, how do you check this? You need to transform characters because in the end, so we're having an expression of this type here. And what you want to do is you now need to say, you need to be concrete about what it means for tau plus 1 and minus 1 over tau. What does that mean to relate them? How do I relate them back to this? That's discussed in detail in the notes, but so there's what you do is there's so-called modular matrices. Modular matrices. The first one is tau, and what it does is it takes chi of, so I'm going to write chi of q, and I'm going to write chi of tau instead. It's really just as simple as up here. There's no magic. So it takes chi of tau and relates this sort of like that. Actually, sorry, this is not quite correct. Nah, it's going to be fine. So what I mean is, so what tau does, actually, no, let's make this. So there's a matrix tau, which takes tau, sorry, there's a matrix capital T, which takes tau to tau plus 1. There's a matrix S, which takes tau to minus 1 over tau. And they have an action. You can also think of them as acting on the characters. So, and their action is really just going to be that the characters are transforming in representations of these, so they span their own group, which is called the modular group. So J in formal families. So this is very fast, and I apologize, but you'll have, I can be a bit more concrete in a minute, like I said. Oops, tau. And then there's the matrix S, which does the other one. So there's J in I, Sij, chi J, and tau. And so here what you see is that these operations that I claimed, so sending tau to tau plus 1, what they do is they take a character and they reshuffle them in terms of characters evaluated at tau, but multiplied by some matrix. So this is basically just like a matrix T acting on a vector chi, if you think of I as vector indices. And that's what these do. They have a number of properties. In particular, tau, T, capital T is very simple. It's almost a trivial matrix. But the one that is super important here, this is the S matrix. And the S matrix, I should say, so I and J are both in the set of conformal families. That means for mathematicians here, in the set of conformal representations. And now we can talk about this here. This is the modular S matrix. And this is an important matrix. So let's just make here the reference. And it is important here for my purposes because it gives rise to something called the Verlinde formula. The Verlinde formula. In the following combination. Oh. Did I black out?
Yeah,
No,
for a
yet
little
not.
bit.
How long
Sorry,
did I
if you
black
may-
out? I'm gone again.
A few seconds.
A
It
few
was like
seconds.
5 seconds or something.
Okay, I didn't say much important. So the important thing is that this modular
Also, you
S
just have
matrix.
10 minutes left, Christian, just that you know.
Yes, right. I'm almost done. Like really hitting the.
Okay.
Thanks for the heads up. So the Verlinde formula takes the fusion coefficients from the beginning of today's lecture, and it rewrites them as oops, this needs to be an L, J, L, and S complex conjugate KL divided by S0L. So this looks like a complicated expression, but this is actually something. Actually, let me write this. No, it's written like this is okay. The structure of this formula becomes more eminent written in the fusion matrices that we introduced. In terms of the fusion matrices, this really is just, so I take the fusion matrix Ni. Remember that the coefficients of this are just these. Let me remind you, Ni, J, K is this. And then Ni, written as a matrix without components, is diagonalized by the matrix S. So that's why this matrix S is so important, because it appears in the fusion matrices. The fusion matrices just carry the representation theoretic data of the conformal algebra. And S is the one that diagonalizes this. So this thing here is diagonal. And it has a bunch of eigenvalues, and the eigenvalues of the fusion matrices, I just said this in the beginning, they furnish representations of the fusion algebra themselves. And importantly, there's one eigenvalue, and that there's an exercise for this. There is one. So I should be concrete. So let's write this. So the fusion matrices commute, right? Fusion, actually, let's just write like this. Ni and J, they commute because they furnish a representation of the fusion algebra, and fusion is commutative. We said that in the beginning, right? So that means that they have a shared eigenbasis. And amongst that eigenbasis, there is one particular vector. There's one vector, one eigenvector, and one eigenvector with with entries, with positive entries. And these positive entries turn out to be the eigenvalues, one particular eigenvalue of the fusion matrices, and they're called the quantum dimension. So quantum dimension. And this is another concept that appears all the time in in topological matter. And you can write the quantum dimensions as follows. So the quantum dimension for a family I, for family I, is just this. And there's an exercise 6.3, where you think a bit about quantum dimensions, and you show that it's related to characters in this fashion. All right, so this is as far as I wanted to get. I didn't want to have to rush as much, but I have at least laid down the most important parts for today, which is fusion, the modular S matrix, the Verlinde formula, which is, let's go back here. This is the Verlinde formula, and partition functions. So, are there any questions? I guess I rushed a bit too much.
What were you saying about how the entries of this all positive vector were related to dimensions?
What you do, well, the first thing you can do is, so to say, you take, say, an I, and it has an eigenvector. So there's going to be some eigenvalue for V. So V is an eigenvector, and J, let's apply to the same eigenvector, has an eigenvalue Nj, and you have, so the eigenbasis, so the eigenspace of these matrices is going to be I-dimensional. So there are going to be several ones. And there's going to be a particular, so this is just a relation, but there's going to be a particular, let's call this vector, what do we call this? V hat, which has as eigenvalue the quantum dimension, V hat. So this is a very special eigenvector. Mathematicians, you can show that there's a theorem called the Perron-Frobenius theorem. And there you show basically that this vector V hat has entries which are the quantum dimensions, d I. Well, let's just write like this, and this is a number of entries, which is the cardinality of the set of conformal families. So if you have 3 conformal families, this vector is going to be 3-dimensional. If you have 5 conformal families, it's going to be 5-dimensional, and so on. So it's the number. So that's what I meant.
Okay, thank you.
And these quantum dimensions, as far as I understand, they appear in topological matter as dimensions of topological Hilbert spaces and so on. But perhaps, so here I'm a bit out of my range of expertise. I don't know much about topological matter in that sense, like quantum computation. But I'm pretty sure we're going to hear about that in next week, in the lecture on topological quantum computation, and maybe also on the non-invertible symmetry stuff, but maybe that there's no reference to it.
Okay, thank you.
All right, so maybe in that case, I feel I rushed a bit. So what are the bits and pieces that I want you to take away from today? Well, first we had this notion of irreducibility, but in the grand scheme of things, you can sort of forget about this. So what's going on? So you're having a state space, this thing, right? And you have a bunch of representations which are allowed, and you can shuffle, you can mix them amongst left movers and right movers. There's not always going to be, so there's no unique solution to these constraints that I told you. There can be several solutions Zi, so they are going to constrain the solution Ci. So maybe what I can add is that at the end of the day, so you have these matrices tau, and you have the multiplicity matrix Z, and it should commute just as S should also commute with the multiplicity matrix. So viewed as matrices in I times I. So they commute, and that gives you constraints. And all that it does is you have a bunch of families, which are the representations of the conformal algebra, and you can shuffle them in a particular constrained way, and that gives you a physical spectrum. And all of this fusion and so on, you can view this as a version of a tensor product. It's not in a strict sense a tensor product. Like I said, the reasons are laid out in the notes, but you can think of it as a product between representations. And that's basically it. So with that, in principle, you should be settled for next week, at least for my stuff.
May I ask a question?
Yes, please.
It's not really clear to me the relation between the interaction strength coefficients and the fusion coefficients, except that when one is 0, the other is 0. But apart from that, it's not clear how they are related.
They are really that's like, in essence, this number captures the most basic data of this. So this guy, the interaction strength, the 3-point coefficient, it carries much more information than this thing. So the fusion coefficient has much less information than the actual interaction strength. Let me give you an example. How would an example go? I didn't really discuss operator product expansions here in the lectures. Let's see. Let's see. Right, okay. From the fusion coefficients, I know that this thing here is going to be 0, and that's basically all I can say. It's either going to be 0 or non-zero. So I cannot make the statement of like there's going to be C sigma sigma sigma. It's going to be proportional to this. And I can only say if this is going to be 0 or non-zero. So it's going to be a yes or no answer. Like from the fusion. Fusion just tells me if this thing is 0 or non-zero. That's it. There's no more information I can extract from the fusion coefficients on the interaction strength. So maybe, yeah, that's all that there is to it, to be clear. Does that already help? Does that resolve the...
Yeah, that helps. And so if a related question then, why is it so relevant or important to know if n is 0 or non-zero, or why is it sufficient instead of knowing the interaction strength?
Oh, that depends much on the problem that you asked, that you're interested in. If you're really interested in an experiment, say, where you're trying to compute the 3-point function, then knowing the fusion coefficient is by far is not enough, right? You really want to know what is this number, right? It will turn out for many purposes that you will see in my lecture, that sort of the fusion structure is sufficient to know which representations appear. Sorry, it's sufficient to know the fusion structure, meaning it's sufficient to know which representations appear, well, in the first place. Like, you don't need to know the interaction strength, but then again, there are many, many important physical problems where you need to know the interaction strength.
I see. Thank you.
Other questions?
Actually, before anyone has an additional question, can you hear me?
Yes, we do hear you.
No. Am I gone again?
No.
What happened? So, oh,
I don't know.
Saskia.
Saskia stopped talking. I don't know.
Okay. I guess she wants to stop the recording. Well, in that case, you can just ask me questions. You can ask me questions on the exercises. You can ask me questions on anything related. Maybe you've peeked into the notes and something wasn't clear, like stuff that I didn't discuss here in the lectures. Just go ahead and you can ask me. You can also write emails to me. And if not, you can just approach me next week when we'll all be in Maynooth. If not, let's see, like who has control over the recording? I don't. Oh, but I am the host. Is there a recording still? Yeah, there's a recording. So let's see. I do. So I'm going to stop the recording now. And so stop.